So today I want to look at we want to study the implementation of this list. Right? Now remember, we're trying to implement an array-based list. So we've got a list that can grow or change size. Right? So the number of elements, you can have 0 or you can have 1,000,000. Right? And you can just add stuff to the list. And as you add elements to the list automatically grows to accommodate those elements. So our implementation today, we're just going to look at a list of ints. Right? So if you want to hold anything else, unfortunately, the only solution we have, if you want to hold a different type, is to copy what we're going to do today and rename everything to a different type, and then go inside and change all of the types. So if you wanted a list of double, you'd basically duplicate all the code we have now, and then change all the int references to int to double, right? And so that's the only way that we know how to make a list of a different type. Right now you also have two different types now. You have a list of int and you have a list of double. Right? Now that's not a great way to do things. So a little bit later, we're going to implement a generic list or generic data types where you can create a list that can hold any type. But you're going to see that that introduces other problems. Okay, so to start with, we're going to separate the implementation into two parts. Right? We want the header file, where we're going to declare the functions that our list supports, and then we're going to have a source code file where we have the actual definition of the functions. Right? So we're going to start by putting in our include yard, right? So every header has an include yard in it. Remember, this is to prevent the header file from being included into a program more than once, right? Because if you include a header file into the same source code more than once, you end up with duplicate definitions of the functions, right? Duplicate declarations of a function, and then the compiler complains, right? Because you have the same function declared twice. All right, so we've got our include yard. I need to include standard bool in this case because I want to use bool as a type. So I want to return true or false from one of the functions. And now I need to tell people, what does this data structure look like, right? Or what is the name or what is the type of this data structure that you're going to use, right? So that's the first thing we're going to do. So I'm going to create a type def here. Right? So there's my type def of something called struct list. Right? So I've got a structure called list. Right? I'm going to provide an alias to that as just plain old list, so people don't have to type struct list everywhere. And now we've got something very different here that we haven't seen before. Right? I've got a type def of a structure, and I don't have the definition of the structure. Right? I've got struct list here, but there's no definition of the structure itself. Right? And so if you read the comment, I spent the last 2 or 3 hours commenting all this code. So if you're looking at the source code that's online, it's going to be missing the comments. Or missing some of the more explanatory comments. A lot of the comments are already there. OK, so what this is an example of what's called an opaque type in C. Right? So the user of the list class, not the list class, the user of our list data type, this is all that they see. Right? All that they see is that there's some structure called list, and they have no idea what's inside of it. Right? And so that's what we mean by opaque. Right? The user can't actually see into the list structure to see what data members are part of that structure. Right? So in other words, the implementation details of the list type are hidden from the user. If any of you ever do software engineering, you'll come across the term information hiding. Right? And so this is an example of exactly that. Right? I'm hiding the information that the list uses as its implementation. Right? Now, the reason I want to do this is because I don't want people going into the structure and manipulating the information that's there directly. Right? So I want to be able to control exactly how this list works. So if you don't actually have the definition of the structure, where is the definition? Well, it turns out the actual definition is going to occur in the source code file. Right? So in list.c, which a user of the data structure may not ever get a hold of, right? So it's possible to distribute just the header files of a C program or of a C library, right? And then you also distribute the compiled version of the C library. So I can compile list.c into what's called an object file, right? And I can just distribute those two things to people. They never actually see list.c, right? So they never see the implementation. All right, so somewhere there's going to be a structure. We'll look at that in a minute. Right, now let's take a look at the functions that we're going to provide for our list. So the first function is this thing called list init empty. Right? And so for those of you who are still, who like Java, this is basically the no argument constructor for a list. Right? So this is the thing that makes a list. Well, makes a list and returns it back to the caller, and it's an empty list. Right? So the caller gets back a pointer to a list. Right? The next function, again, if you like Java, this is another example of a this would be the analog of another constructor. So this one makes a list that can hold that many elements. Right? So when the user gets back the list that's returned by this function, it's guaranteed that they can put this many elements into the list without having to do anything, without the list resizing itself. Right? So again, this returns a pointer to a list. Here's a function that copies an existing list. Right? So it makes a copy of a list and returns the copy. So again, if you like 124, this is a copy constructor. Right? Or this would be the analog of a copy constructor. Right? Takes in another list. Notice that other list is const. Right? So remember what that means. That means people can't modify that list. Right? So that means the function promises not to modify the incoming list. Right? Because it's declared as const. Right? And it returns a copy of the incoming list. Okay, so what else would be useful for a list? Well, it would be useful for the user to be able to know how many elements are in the list. So that's called size. Right? Again, notice all the functions start with list underscore. Right? Because I need to make sure that all of the functions that appear in my program, they all have unique names. Right? So this is very common in C, where if you have a data type called blah, then all of the functions are also called blah underscore something. Right? And that's to try to attempt to make sure that all of the functions actually have unique names. Right? So this one takes in a list, right, and tells you how many elements are in the list T. Right? Okay, so what else do you want to do with the list? Well, you want to get an element that's stored in the list. How are you going to get the element? You're going to get it by index. Right? So here's our function get. Right? So it gets the element from that list, right, that's at that index in that list. Right? Notice the documentation says that if you use an invalid index, you get undefined behavior. So we'll see how we deal with invalid indexes shortly. Right? What does this return? Oh, this returns the element. So it returns an int, right? So it returns the element stored in the list. Okay, set replaces an element in a list, right? So it replaces an existing element in the list, and it returns the value that was replaced, right? So it returns an int in this case, right? So setting an element in the list T, right, at that index replaces the element at that index with that value right there. Right? The add function adds an element, right? Adds that element to the end of that list. It returns true if adding the element succeeds, and it returns false otherwise. Now, when you add to a list that has an array that's already full, right, we have to resize that array, right? So that's why this function can fail, because if resizing fails, then we can't add an element to the list. All right, here's insert. Right, so we're going to insert an element into that list. So we're going to insert that element into that list at that index. Right? Now remember how insert works. Right? So if I'm going to insert into the middle of the list, I have to take all the elements to the right of the insertion point, and I have to move them one down to the right. Right? So it looks like I'm going to have to use a loop or something else to move all the elements one position over. Right? And then I can add the element into the middle of the list. This function also might cause the array to resize. Right? So if the array is full and I insert something into a full list, right, I have to resize the array and then insert the element. Remove removes the element at that index from that list, and it returns the element as the return value. Okay, finally we've got a toString function. This is uncommon in most C library APIs. It's only here because I teach 124. So, right, and in 124 there's a toString and it's super handy to print stuff out. It's actually fairly uncommon for functions like this to appear in a C library. If you want to print something out, normally you have to do it yourself. But here I've decided to include a toString function. So this returns a string representation of that list. Right? So notice that the string is returned as a pointer to car, right? Because strings are just arrays of characters. Now you're going to see when you implement this one, well, it's not so bad to implement. There's a different way that you can let a user get a string representation of the list. So the problem with this function here is that every time someone calls this function, we have to allocate a bunch of memory for the string, right? And then return a pointer to that array to give them back the string, right? Now, if you're printing something out in a loop or you're printing something out a lot, right? You're allocating memory, you're printing it out, and then you're probably done with the string. So then you have to deallocate all the memory that was given to the string, right? And so that's actually wasteful, right? Because you're constantly allocating and then deallocating memory, right? Just to print something out. If you're using C or Python, that's just the way it is, right? You end up allocating and deallocating memory, even though you don't see it as the programmer, right? That's just the way things work, right? C programmers kind of don't like that sort of thing, right? Because they're more, one of the reasons to use C is for its efficiency. So there's a different way to do this. The other way to do this is for the caller to allocate memory for the string, and then for the function to write into that string. So list to string 2 is that function. Right? So it produces a string representation of a list T, right? Storing that string in a pointer that's provided by the caller, right? And the caller, because they're providing the function with an array, the caller has to tell the function how big that array is, right? So buff size is the size of that array. I don't know if we'll get that far in class today. And then finally, we have a function that frees the memory that's allocated to the list, right? So way back at the beginning, when you make a new list, right? So when you make a new list, this function has to allocate memory for the list. It may have to allocate memory for whatever's inside the list, right? But remember, whoever's using the list, they don't know what's inside the list, right? So there's no way for the person using the list to free the memory that's part of the structure here, right? Because they don't know what's inside the structure. So if you're going to do this sort of thing, you've got to provide a function that will actually free the memory that's associated with the list, right? So we've got this little function here at the end. All right, so we've got a lot of functions to get through. Anyone have any questions so far? All right, so first thing we're going to do is what's inside of this list. Right? And so here's the beginning of our source code file list.c. Notice that there's a whole bunch of includes here because I need all of these header files for certain things in some of these functions. Right? Notice that the last thing that we include is the header file list.h. Right? So we're going to include that header file so that we get the definition, well, the declaration of that type, of that structure, and the declaration of all of our functions. Oop, oh, sorry, wrong one. Here we go. Okay, so here's the actual structure. Right? So our structure, our list structure. So we're going to make an array-based list, right? So what do I need to hold a bunch of ints? Well, I need an array of int, right? So there's my array of int, right? So I don't actually have an array here, I just have a pointer, right? But that pointer is going to point to the first element of the array, right? Now, what else do I need to know in order to implement this thing? Right? So I need to know, well, how many elements are actually in, well, I need to know how big is that array, right? So I need the capacity of that array. Right? So I'm going to store that as a member. And then finally, I need to know how many elements are actually in the list, right? Because the size of the array is different than the number of elements in the list, right? And so the size, that's going to be the number of elements in the list. Right? And so if you're doing this in Java, this would just be a class, right? Class array list, right? It would have an int array as one of its fields, right? Because it's Java, you wouldn't store the capacity because the array knows how big it is in Java, right? But you would store the size, right? The number of elements that are also in the list, right? So this would just be an int field in Java. Right? So you can imagine that this structure here is just a primitive type of class. Okay. So I'm going to create this variable called, this constant called default capacity. I'm going to set it to 4. That's just the default size, the default capacity of a list. Right. We'll come back to this thing in a second. Right. And now we're ready to start implementing our functions. So here's the function that initializes an empty list. Now remember, I also have a function that initializes a list of a specified size. Right. That's the next one. So I'm going to be lazy, and I'm just going to call that other function for list init empty. Right. So to initialize an empty list, I need to initialize a list of size 4. So I'm just going to use the other function for that. So this is where things actually start to get interesting. Right? Okay, so number 1, I need to return a pointer to a list object. Right? So I need to actually allocate memory for that list object. Right? So the first thing we do, right, is I make a pointer to a list, right, and I allocate memory for that list. Right? How do I allocate memory for the list? Well, I use malloc. Right? How does malloc work? Well, malloc needs the number of bytes, right, to allocate. Right? So how big is a list? Well, I can use size of list to get the size of a list structure. Right? So when you use size of list, it's going to go to your structure, and it's just going to be the size of a pointer. So that's probably going to be 8. It's going to be the size of whatever size t is. That's probably also 8. And then the size of that. So that's also 8. Right? So the size of a structure is just the size of its members. It's just the sum of the size of its members. Right? It is at least that big. Okay, so there's our pointer to a list. Right there, right? So remember when I allocate memory for something, it gives me a chunk of uninitialized memory, right? So I've got a pointer I've got a chunk of memory that's big enough to put a list in it, but I don't actually have a list there yet, right? Because I have to fill in all of this stuff now, right? So now I have to manually go in and I have to make an array, I have to set the capacity, and I have to set the size. Right? So I need to make an array. Right? Now my array is supposed to be at least that big. Right? So how do I make an array of int that's at least that big? Well, I just use malloc again. Right? I guess I should remind you why we're using malloc here. So you might ask, well, can't I just make an array? Right? So can't I just do something like int a capacity? Right? So can't I just do that and then assign it or do something or try to assign it to my pointer that's in the structure? Right? And the answer is no, right? Because this is a locally allocated array. Right? As soon as this function's over or is finished running, that array disappears. Right? And the memory for that array disappears. Right? So we can't have that happening because now your list doesn't have an array. Right? Whatever array you just had now disappears. So we can't do that. Right? You have to dynamically allocate that array. Right? So we use malloc. Right? Again, how does malloc work? Well, you need to specify how much memory do you allocate, right? In units of number of bytes. Right? So I want that many ints. Right? So the total amount of memory is the capacity times the size of one int. Right? And so now I have an array that can hold capacity ints. Yeah, question at the back.
Is it any disadvantage
To always using malloc. Yeah, actually there is. If you only need a local whatever, either a local int or a local array of ints, then you should use the local int or local array of ints. So when you dynamically allocate memory, that memory is slower than memory that's locally allocated. Yeah. There's also a price you have to pay, right? So you have to call a function, so that takes time. The way malloc works is it calls the operating system memory manager. So that's probably going to cause your program to stall while the operating system swaps something in and out. And then it has to return. And then you have to free it later on. So that's the big problem, I would say, is that you have to free it, remember to free it later on. Right? If you forget to free it later on, you have a memory leak. OK, now I've got two mallocs here. Either one of them can fail. Right? So I have to check the return from both of them. Right? So if T is null, or if the array is null, then mallocs failed to allocate enough memory for the list. Right? So here, we're going to return null. Right? And so here you have an example of a function that returns null to indicate an error. Right? So this is one way to indicate an error has occurred in C, right? Is to use the return value to indicate that an error has occurred. The problem with using a return value to indicate an error is that the caller has to look at the return value. Right? There's nothing forcing you from looking at the return value. Right? So for example, here when I malloc something, there's nothing that forces me to look at whether or not the pointer is null. Right? I can just ignore it and keep on going. Right? So one of the problems with using, so that's the main problem with using a return value to indicate an error. Right? The caller is free to ignore the return value. So they may never know that an error has occurred. OK, so I've got my list. Right? I've got T. I've got my array. So now I can go ahead and fill in all of the members of the list. Right? So remember, T is a pointer. So if I want to get to a member of that structure, right, I can use the arrow operator. Right? So the array that belongs to T, right, I can now assign ARR to that. Right? The capacity of my list, right, well, it's just that. Right? So I can assign that. The size of the list, that's the number of elements, right? So I can assign 0 to that, right? And there's your empty list of a given capacity. All right, any questions there? Right? I think we will all agree, right? This is much harder to do than what you would have to do in Java, right? So in Java, you would just make an array of size capacity, and that would be the end of it, right? You'd be done, right? Here, you've got to do all this stuff. Right? So things are, they're not harder. It's just that you have to do everything in C. Right? Whereas higher level languages like Python and Java, they try to save the programmer. They try to do things for the programmer. Right? OK, what about copying another list? Right? So if you think of copying another list as just being a copy constructor, then you can sort of go through all of the same steps that you would go through in Java, right? So if this is just another constructor, I'm basically going to repeat what I just did before, right? I'm more or less going to repeat this, right? And so now that I think about it, I really should have called this function here, but I didn't. So I just copied and pasted all the code. So that's bad. Don't do that, right? I really should have just called the other function and made a list of the appropriate size, right? So the list of the appropriate size, right, that would just be other capacity. Right? So here, once again, right, allocate memory for the list. Right? Allocate memory for the lists array. Right? This array has to have the same capacity as the other lists array. Right? So I'm going to get that by looking at other capacity. Again, check if T or ARR is null, right? And if they are, the function's failed. There's nothing I can do about it, right? OK, now, right, if I reach this line right here, so if I reach line 57, right, I'm now in the situation where I want to copy the elements from the other lists array into T's array, right? And so I could write a loop. So in other words, I could do the following. Right, so for int I equals 0, I is less than, okay, so how many elements do I have to copy? I have to copy other size elements. Right, and now how do I do the copy? Well, it's pretty easy. It's just TARR I. Whoa, sorry. Equals other ARR I. Right, and that would be perfectly fine. Right, that does exactly what we want it to do. Right, it copies the elements from the other array into T's array. Right, and that's fine. So that's definitely one way to do it. But there is a function in C that will copy a chunk of memory for you, and that's exactly what we want to do here. Right? And so that function in C is called memcopy, and not surprisingly, right? Copies memory. Right? Okay, so let's look at what memcopy does. Memcopy is a bit weird because it's actually you would think it would be not defined. You think it would be declared in standard lib. Right, because standard lib says that's the header file where memory management, where the memory management functions are declared. It's a bit odd. It's declared in the strings library. It's declared in strings.h. So it's actually declared in the string part of the standard library, which is strange. But it turns out you have to, because strings are just arrays of characters, you have to copy a string, you end up copying arrays. So they put it here. Okay, so memcopy we're using, which one are we using? Sorry. Memcopy 1, 2, 3, 3. Okay. 1, 2. Oh, I see what's going on. Okay. So we're actually using this one here. I haven't told you what restrict does, but there's a reason why I haven't told you what restrict does. It's because it's not actually useful for the programmer. Restrict is something that you can tell the compiler. Restrict is something that the compiler can use to optimize the code that's the machine language code that's generated for the function, right? Which we don't really care about in this course, right? So as far as we're concerned, you can just ignore restrict, right? So this one takes in a count, so we'll have to look at that carefully, right? It takes in a pointer, right? A void pointer, right? Called src, so that's source. Right? And it takes in a void pointer to something called dest, right? Destination. So this copies memory from the pointer pointing there, right? Into whatever memory this pointer points at. Right? So this can be an element of an array, a pointer to some element in an array, right? And that can be a pointer to some element in a different array. Right? It can also be a pointer to some element in the same array as the source. Right? So if you look at the documentation, where does it go? Somewhere it says it's allowed, yes, it says it's allowed to overlap, or is that the other one? No, that's memmove. It doesn't matter. So memcopy is the same thing. So the pointers can be pointers into the same array. Okay, and what does count do? Now you might think it's the number of elements, right? But it's not. Right? The reason it's not the number of elements is because the pointer here, right, is a pointer to void, right? So it's a void pointer, right? Now remember what a void pointer is. Void pointer can point at anything, right? But the compiler doesn't know what it's pointing at, right? So there's no way to know that it's pointing at an int or a double or something else. So this count, if you read the documentation, says copies count characters from the object pointed to by source to the object pointed to by dest. Right? Both objects are interpreted as arrays of unsigned char. Right? So that count is the number of characters, right? Or the is the number of characters, right? But we've got an array of int. So when I use memcopy, I have to take the number of int elements I want to copy and multiply it by size of int, right? Which is here, right? So how many elements do I want to copy from the other array? Well, the other list has other size elements in it, right? I have to remember, okay, but this is not the number of ints, it's the number of characters, so I have to multiply that by the size of int. Right? Now, where do I want to copy the memory from? Well, I want to copy it from the start of the other array. Right? Where do I want to copy it to? I want to copy it to the start of t's array. Right? And so that's how you use memcopy to copy a chunk of memory from one array to another. Let me just quickly check memcopy here. Oh, sorry. Memcopy cannot copy into the same array. You have to use something else. That's why I have another tab open. So memcopy copies from one array into another array, but it can't copy from the same array into. It can't copy from the same array if the two chunks of memory, if the area that would be copied overlaps. Right. Oh, sorry, that's not it. Where is the overlapping part? Normally, oh, here it is. All right, well, let me look at that later on. Next. Oh, okay. Now to finish off the copying, you have to copy in the capacity and the size, right? So the size of this list is just this. Sorry, the capacity of this list is just the capacity of the other list, and the size of this list is just the size of the other list, right? And then don't forget to return t when you're done, right? So return the copied list. All right. Now what about the size function? So the size function is a lot easier, right? We have a field that actually, sorry, we have a member in the structure that actually stores the size. So we can just return that member. Get is also straightforward, right? Because you're just getting an element out of an array, right? So to get the element in the list at that index, right, you just need the element in the array at that index, right? So again, use the arrow notation, right, to dereference the list t and to get to its array directly. Right? Now, we should do something to indicate that an error has occurred if that index is invalid. Right? And so for get, I'm going to use assert to test. Is the index, in fact, less than the size of the list? Actually, that's not complete either. Right? Right? So the index has to be less than the list, less than the size of the list, and the index has to be greater than or equal to 0. I guess that's the correct assertion. Right? So I want to assert that this condition is true. Right? If that condition is false and assertions are turned on, then assert will cause the program to stop if you call this function with an invalid index. Right? So this is another way that you can use to indicate that an error has occurred. Right? You can crash somebody's program, right? Which is what assert does. Right? Assert causes the program to stop. Okay, I guess I should fix set, because set also should use the same assertion. Okay, so set an element in the list, it's the same thing as get, right? You just have to set the element in the array. So to set the element at the given index, right, you can just write t arrow array index equals elem, right? That sets the element at that index to that value there, right? But our definition of set is similar to the Java definition of set, right? It returns the value that used to be, that you just overwrote, right? So to return the value that you overwrote, you have to remember what is the value that you're overwriting, right? So before you actually set the element, right, create a variable called old, get the current value, right, and then return the value of old at the end of the function. All right, here's add capacity. So add capacity, that one is not in our header file. Right? So if you look through the header file, right, there's no function called add capacity. Right? So add capacity appears inside the source code file. Right? And so what that means is if you're not distributing the source code file, right, people who are using your list don't actually know that this function exists. Right? So this is a way to attempt to hide the fact that there is this method here, this function here, right? So this would be sort of the analog of a private method in Java. Right? So add capacity is the function that grows the internal list, right? Sorry, the internal array, right? So if we run out of space in that array, add capacity is going to increase the capacity of this array, and it's going to copy over the elements from the old array into the new array. Okay, so let's look at how that works. Okay. So if I need to increase the size of the array, I basically need to allocate memory for a new array, right? So I can use malloc again if you wanted to, right? You can use calloc if you wanted to, but you should remember that there's a realloc function, right? And just to remind you what realloc does, right? Realloc reallocates the given area of memory, right? It says some other stuff here, but that's fine. Where is it? There's, so the way the reallocation works is, right? Realloc attempts to expand or contract the existing area of memory if possible, right? So in other words, it takes your array and it tries to expand the array in place, right? If it can do that, then all of the elements that were there are already there, right? So that's good, right? Now, if it can't allocate that memory in place, then what happens is it actually calls malloc to get you a new chunk of memory, right? And then it copies that memory into the newly allocated memory, right? So realloc does all the copying for us, so we don't have to worry about copying the old elements into the new array, right? Just call realloc, right? So the way realloc works is you pass it the pointer to the memory that you want to reallocate, right? So that's just the array. And you tell it, how much memory do you want, right? Well, I want at least that much plus 1, right? Because I need at least one more chunk. I need at least enough memory for one more int, right? But instead, I'm going to double the existing capacity, right? Again, read the documentation for realloc. You'll see that the units of memory are in sizes of char, so I have to multiply by the size of the element type, right? So I have to multiply by the size of int here. If that succeeds, you get a new pointer, right? So you get a pointer to the newly allocated memory, right? If it fails, you get null, right? So if new array is null, I'm going to return false to indicate that we can't actually add any more capacity. So here's another example of a function that uses a return value to indicate an error has occurred. Okay, so if this succeeds though, you've successfully reallocated, or you've successfully expanded the size of the array, which is great, right? But now I have to update some things, right? I have to update the actual capacity, right? So I have to take my capacity for t and multiply it by 2, right? And then I have to make sure that the array that the pointer to the array that I used to have, I have to now make that point to the new array, right? So that now points to new array, right? And once I get here, I can return true, because I managed to allocate enough memory for the new array, right? And so there's your little function this function you can always use, right? So if you ever need to reallocate memory for an array, this always works, right? This is basically the standard way to do it, right? All right, so once we got that function settled, worked out, we can actually go ahead and implement any functions that might have to reallocate the array. So that would be add and insert. So add takes that element and tries to add it to the end of that list, right? So ignore the if statement for now, right? Let's assume that there's enough memory in the array to add the element, right? So what do you have to do? Well, the array has sufficient capacity already, so all I have to do is set the element in the array at t size, right? Because t size, the last element in the array is at index t size minus 1, right? So the next free element in the array is at t size, right? So just set the element at t size to that element, right? Now, the thing that's easy to forget is you forget to increase the size of the list by 1, right? But I just added an element to the list, so I have to increase the size by 1, right? And then return true to indicate that this worked, right? Now, this is fine, assuming that you have capacity, right, in the array. If the size of the list, though, is equal to the capacity of the array, you don't have space in the array, right? So what do you have to do? Well, I have to add capacity. Fortunately, we just wrote a function that did that, right? So I can just call a function, add capacity, right, to increase the size of the array and copy all of the elements from the old array into the new array. Right? If that works, or if that doesn't work, right, I have to return false to indicate that add failed. Right. Okay, any questions so far? Yes? No? No? Okay. Insert is, I guess it's similar to add in that you have to check, is there actually space in the list, in the array for the new element, right? So we'll do that in a second. Insert, though, you have to shift a bunch of elements to the right, in order to make room for the inserted element. So we'll have to see how to do that in a second. Okay, so insert takes an index, so we have to validate the index, right? Again, I did it incorrectly. So if index, assert that the index is greater than or equal to 0, and now here the index can be equal to size, right? Because you, if you remember back here, inserts, oh, here. So note that using an index equal to the size of the list adds the element to the end of the list, right? So insert's a bit odd in that it takes, it can't accept an index that is technically invalid, right? But that's easy to check for. It's just instead of less than, it's just less than or equal to, right? Now, if someone uses an index that's equal to the size of the list, right, that's just adding to the end of the list, right? But I've got a function that adds to the end of the list, so I'm just going to call that, right? So we just call add and add to the end of the list. Okay, if someone uses a valid index that's not at the end of the list, right, then that's where I have to do the insertion, right? So I have to check, is there actually room for this element in the list, right? If not, again, I have to grow the list, right? And if I can't grow the list, I have to return false, right? Okay, now you get to this point here, right? So I've got room in the array. I need to shift a bunch of elements to the right one position. Right? So move all the elements from index and beyond one position to the right. Right? Again, you can write a loop to do this. Right? You start at the end of the array, and you just move elements one over, right? One to the right, starting from the end. Right? You can't start from the front, because if you start from the front, you overwrite elements. You overwrite existing elements in the array, so you don't want to do that. Right? So you start from the end, and you just move elements one over to the right. So you could do it that way. But there's a function called memmove that will move a chunk of memory for you. Right? So if we go and look at memmove, right? Memmove says it copies count characters again, right? So not ints or doubles or something, right? It always moves characters. So it copies count characters from the object pointed at by that to the object pointed at by that, right? Okay. So here the objects may overlap, right? So in other words, you can move memory from an array into the same array, which is what I want to do, right? I want to take these elements and I want to shift them one to the right. Right? And so I need to provide how many elements do I want to shift, right? Multiplied by the size of the element, right? That is the index into the, well, that's a pointer starting at where I want to move, right? And that's a pointer pointing at where I want to move them to. Right? So once you've got all that straight, implementing this is very easy to do. Right? So I want to move. Oh, how many elements do I want to move? Right? So if I'm inserting at that index, right, then the number of elements I want to move is equal to the size minus that index. If you just sit down for a few seconds and work that out, you'll be able to convince yourself that that's correct. Right? So I need to move that many elements. Right? Remember that memmove takes, the count is actually the number of characters, so I need to multiply that by size of int, right? Because I have a list of int. Right? Now, where do the elements start? Where I want to move? Right? Well, they start at that index there. So they start at T array index, right? I need a pointer to that element. So I can just take the address of that element instead. Where do I want to move them to? Well, I want to move them 1 to the right. Right? So what's 1 to the right? Well, that's just index plus 1. Right? So again, I can just write T array index plus 1 and then take the address of that element like that. Okay? And that successfully moves everything 1 over to the right. Once you moved everything 1 over to the right, you go ahead and insert the element. Right? So at index, right, we add the element called elem. Right? We just inserted something into the list, so don't forget to increase the size of the list by 1. Right? And everything's worked out. So we've done everything we need to do, so now we can return true. And so that's how you insert an element into the middle of the list. Yes?
What package is all the mem moves?
Mem moves, so all the mem moves are in string.h.
Why didn't we need the ampersand to dereference the pointer before?
Ampersand doesn't dereference, right? Ampersand is address of. Right? So T array index plus 1, that's actually the element at index plus 1 of T array. Right? So if I take the address of that, that gives me a pointer into the array at that index. Yeah. There are other ways to write this. This isn't the only way to do this. Right? Okay, so why don't I just do it? And then, well, okay, so we got like 1 minute. So there is another way to do this using pointers directly. Okay, so T array, TARR, right? So that's a pointer to the beginning of the array, right? If I want the element, if I want a pointer to the element at index plus 1, I can just add index and then plus 1. Right? So you can write it that way if you want. I think, so once you get used to pointers, I think most programmers would write it that way. Right? If you're still used to thinking about arrays, this is okay too. They end up doing the same thing. Right? But you can write it either way. Similarly, this one you can write as, whoa, no, you can't do it that way. Where to go? T ARR. So remember, that's just a pointer to the start of the array. If you want to move to, or if you want a pointer to an element at index, just add index. Sorry, and away you go. Right? So both are fine. Yeah, I mean, both are fine. Right. Any other questions? All right, so we'll do remove and toString in the next lecture. Oh, no, wait. Don't forget on Monday you've got a quiz. Right? So we'll do the quiz on Monday, and then, oops, sorry. And then Wednesday we'll come back to this.